we are setting up a little job on the Mazak here, and I want to show you something a little bit about these machines and some of the issues you have with this type of machine with the Integrex. Well, probably with most multitask machines, when it has to do with the chuck and interferences with the chuck and the cabinet and things like that you're going to do. So let me turn the camera around and we'll look at this and see what the issue is with this little part that I'm doing right here. Piece of material I have chucked in the chuck right now. It's a 6-inch diameter piece of 17.4 pH. And what I want to do, let me jog the C-axis here a little bit to get it oriented properly. This part, it has an API thread on it that comes back to about here on the part, and then I want to put, it has two 3/8/16 tapped holes with some spot faces on the flange of it. And I'll show you a model here on the computer so you'll understand this, but I have to get back here. I want to turn this thread and turn the OD of the what I'll call the flange part of the part, and then I want to put the two spot faces and the holes in this operation, and then turn it around and chuck onto that bigger OD that I turned here, and turn this. There's an Acme thread. I think it's I'd have to go look. I'm not sure. Maybe a 6-pitch Acme thread on the other end of it. And I have to bore a counter bore and everything in here too, and drill it through as well, which isn't a problem. But this OD work, the milling work on the OD is kind of a problem. Let me kind of demonstrate that here. I'll put something in the spindle of the machine. So let me get this down here. You have to orient the spindle and clamp it here. And I'll just put this hammer indicator in here so we kind of get an idea of a tool. I'm going to index the B axis to 90 degrees, or up and down, straight up and down. This index is real slow when you have the doors open. I guess that's a safety feature. Normally that index is quite a bit faster than that when the machine's running. So I've already touched off where I wanted my part 0 when I started this setup here, which would be right about here, of course, on the end of the part. But then I have to go back so many inches back here. I think it's 4. Let me go check. The holes are going to be 4.970 back, but already I'm at about 4.5 inches back in Z. But you can see my issue up here. Let me get the camera closer and you can see here. You can see the issue I'm having here. I'm not back all the way. Let me see how far back I can go, because see, if I have a tool that's about this long to get down to my hole here, everything clears here with the face of the spindle, but right up here, you can see I'm very close to the cabinet and I'm not even at my hole location yet. Let's see, let me carefully jog it till it's almost touching there and see where I'm at here. Okay, it's just about touching right there. And see, I'm only at 4.88 and the hole is at 4.970 back. So the only way I can get around this is I got to move the x-axis up so this is above this sheet metal piece on the machine, which if we do that, we're up here. Okay, that would clear it right about there if I was at that spot. And then I can go back to my, okay, that's about where the location of the actual hole is. But then I have to mill this spot face, so I'm going to have to move back a little bit further. Let's say, I don't know, about 5 1/8 back. And see, I can't clear this part of the cabinet. In fact, this is cut away here because this has been dented before, hitting up here by somebody else before I owned the machine. And this sheet metal was kind of bent over here. They probably had it behind here and moved in or something, and I just cut it off because it allows coolant and shavings to fall off of there anyway better. But this is the issue with these kind of machines. So let's get a tape measure here and see the minimum length tool we could have to get down here. Well, if we were going to drill the hole, we would have to have a tool at least about 12 inches long, which that wouldn't really be a problem for the drill itself, but the end mill, the tool with the end mill to mill the spot face would have to be, at least about 11 inches long. And the machine would probably do that all right, but I kind of like to be closer up, and I don't like to be so close over here to this colliding with the machine up there. And then if you look even higher up here, you can see this area here is pretty close to hitting, this is the door for the tool changer. So I think what I'm going to do to sort of get around this is I've got some taller soft jaws that are about this much taller. They're about an inch, a little more than an inch taller than these. They're about 5 inches tall. Put me about right here, and I can chuck onto this part. I want to chuck onto here a little bit of this part, and in these hard jaws, this would hold fine. It doesn't look like there's, if I jog the C-axis here so you can see, but in these hard jaws with these serrations, when I chuck down real hard on this 4-jaw chuck, this part isn't going to go anywhere like this, and I would have liked to run it like this, but with this issue up here with my clearances, I can't really, and so I'm going to have to put some soft jaws on here and bore them for this 6-inch diameter, and I can move the part out. Like I say, the jaws are 5 inches long, so I can move the part out a good inch. I want to chuck onto about an inch of the part, of the stock, I should say, not the part. And this should work fine. And then I can slightly rebore the jaws for when I flip it around to do the other end, the Acme thread on the other end. So this is the kind of issues you have with these multitask machines, and this is why you don't want too big a diameter of chuck, because right here, if you had a big diameter chuck, like this machine originally came with a 21-inch chuck, which is about this big in diameter where my hands are. This is a 16-inch chuck, so 21 inches, probably that much bigger on the radius than this chuck. And you get into the same issues. You're hitting the spindle on the chuck jaws or whatever you're doing if you're doing a small diameter part. For large parts, it's not really a problem. But for smaller ones like this, well, this is small for this machine in reality. Although I have a little like manual 3-jaw chuck that I chuck into some soft jaws with a dovetail on it. You may have seen that in some earlier videos of mine, and I actually run even smaller diameter parts on this big machine. It's not really a problem. It's just that you have to project the thing out here to get down to the small diameter, or you're hitting the spindle face on the chuck and everything. They usually go on a lot easier than this. I'm not really too worried about the jaw sticking out. What you do have to consider is when I turn the part around, which I do want to do in this case, man, those are tight. And let me snug these screws up by hand here a little bit, and then we'll look at this. When I turn the part around, and I want to chuck onto that, this bigger OD is 4.44 inches back from the flange part of the part. So see, I wouldn't be able to clear that if I get into interference problems here. So let me think about this a second. Unfortunately, these jaws are offset this much. Let me look over here and see if I have a different set of jaws that might work better. See, these go on here like this, and this inside of the jaw, I could bore it a little bit if I need to clear, but I can just take a little bit out of here to get to my 6-inch stock size, and I can make things clear better because the offset is a different direction. Like, I could turn these around, but then I'd have to put bevels on them like this. So I think I'm going to change to this different set of jaws, even though I bored them for a different operation, or a different job, I should say. But take too much out of these jaws, so I want to bore. The stock is 6 inches in diameter, so I got to move the jaws back a little bit. Disc is some sort, like a drop over by the saw maybe. I'll put it in here and we'll chuck onto it so that we have some force on these jaws, because like I said before in other videos, every chuck that exists has a little bit of play of some sort in its master jaws, and when you chuck onto something, the jaws get kicked out a little bit. So if you just bore them without some kind of actual chucking force on the chuck jaws themselves, when it chucks, they'll spring out, and you'll be just chucking on the very back of your counterbore on the stock, and it won't be a secure way to hold the material. I forgot that I had these pins that I could stick in the jaws here. I made these a while back so you could stick one in each jaw, and I have this ring, I should say, that I can chuck onto. The bore of this is just about exactly 6 inches, so I'll have to cut into the ring a little bit, but it's not that big a deal, you know. I'll just bore the ring as well, and so I'll have to get this more or less centered a little bit here. You can look at these kind of keys in relation to these grooves in the face of the chuck and get it in kind of close, and then I'll run a dial indicator on it here to indicate the ID of the ring here, and that'll be good enough for the purpose of boring the jaws. It doesn't really have to be because this is a 4-jaw chuck. I'll be able to indicate the part, and I'm just looking at these keys on the chuck jaws and kind of eyeballing them about the same for right now. I got to go get the indicator. Oh, here it is, right here. Put it in the spindle. Then I can indicate things in here. See, we got about 25 thousandths on the indicator, 25 thousandths on that jaw. If we rotate 180 degrees to get the jaw opposite, we've got about the same situation, same reading. If we look at this jaw now at 90 degrees to that jaw, so it's reading around 0, and the one 180 from it's reading around 0. So I'm going to let that go like that. We're going to bore the chuck jaws like that. If we look at this ID of this ring, measure it at 1 inch over here. See, it's roughly about, it's a little bit less than 6 inches. And we're going to change to tool number 4. It's the kind of this long boring bar that I had set up from a previous job, the super duplex job actually. It's kind of a little bit long, but it'll work for this. So we're gonna let's move it over to Y0. We'll move it up to the part close. I've got to kind of look at this. I've been thinking about this. I think I may bore the jaws to the finished size, because I got to open the doors here to look at this. On this 4-jaw chuck, because there's not too much difference in radius between the finished size of 5 3/4 inches and 6 inches of the raw stock, that I'll move the camera here so I can kind of let you guys see what I'm trying to do here. Be careful not to turn the spindle on with the camera like this. Okay, I've been thinking that I'm going to bore it to the size that's, trying to see it here. Let me get the flashlight. Trying to see where the tool is here. I want to set my 0 point. I may have to get a feeler gauge here. I want to set my 0 point on the jaw itself so that I know how far I'm going back in there. I think like I said, I was thinking to bore these the finished size of the part, because the radius difference between 5 inches and 6 inches, or 5 3/4 and 6 inches, is so small. The 4-jaw chuck, I can just adjust the jaws. I want to set the tool because I want to bore a specific size. So that's 10 thousandths in Z. So set my work offset in Z. Teach minus 0.01. That should put me 10 thousandths. Okay, that's good. Now I'm going to go down to where I would take kind of my first cut here and start the spin going forward. I'm just going to manually do this, kind of 0.1. Let's try that. Okay, that might be all right. Like I said, we need enough shoulder down here for the face to come up against when there's a chamfer on the front side when I turn the part around. And it's going to be close, but I think there'll be enough there for that. So let's continue on. So we just have just enough shoulder there. There's, like I said, there's a chamfer It's probably about like this much on the part, and there'll be a little bit of a shoulder for it to hit up against when I turn it around the other side. And the radius, when this moves out to the 6 inches, won't be enough of a variation to make a difference, I don't think. So let's see how the raw stock chucks in there. And if that works, then we'll just go from there to turn the first side. And we won't have to rebore the jaws. In fact, we could even just turn the first end, and if we set it all up, flip it around and turn the second end and finish it one part at a time without having to do all the parts on one operation. That might be a good idea to get a first article that way. Here's a look at the simulation in Esprit, just so you can see what's going to happen when we machine it at the machine. And the only real particular thing here is this API thread on the OD there. I wanted to explain a little bit about what insert you should use and why you should use it on that particular thread. There's some details that you have to kind of keep track of when you're doing that. And then these holes on the OD, if you remember, we had to move things out away from the chuck a little bit to get clearance on the y-axis of the machine on the cabinet above the chuck. So it's a relatively simple program, but there's these little details you have to consider when you're machining this on this type of machine. So that's the first side of the part. And when we get into that thread on the machine, I'll talk a little bit about the gauge and how you use it. I want to talk a little bit about this particular API thread. This is a B-038R pin end thread form drawing. I've kind of masked off the rest of the title block and these notes that are on this drawing because they don't really apply to what we're trying to show, or what I'm trying to show here. But there are a few things that we got to pay attention to here to cut a thread like this. We have to pay attention to this thread height, which has got only a total of 3 thousandths tolerance on it, which is the height from the bottom of the radius to the imaginary intersection of the pitch in the center line of the pitch of the thread here. And there's only 3 thousandths tolerance there. So if you were going to do this without a full profile insert, which I guess it's possible, I've never done it that way myself. I don't thread these kind of threads that often, so I prefer to do it with a full profile or topping insert, because these radiuses, it'll cut these radiuses, 0.38 millimeters in this case. This whole print is dimensioned in millimeters, but the real dimensions on these threads are actually in inches, because this is an American Petroleum Institute thread, really. But be that as it may, this all works out the same. So if you machine this part to these actual dimensions, they've given this 4.5 inches, which is the typical dimension back on this kind of thread, but you got +0, minus 118 thousandths in this case, or minus 3 millimeters. And I kind of like to run this more towards in the middle of the tolerance somewhere here, and in order to do that, you won't, if you machine everything else to these dimensions, the insert won't top the thread, which is very important for it to top the thread in this case to cut these radiuses, like I've said. So what I have found I needed to do is add stock to this taper on the OD of it, so it'll top the thread, and then I can run this 1.5 millimeters up here, shorter, or in the middle of this 4.5, +0, minus 118 thousandths tolerance, and get the insert to top the thread. Otherwise, like I say, you won't get this close thread depth correct. So I've found you got to add, well, ideally you add about 7.5 thousandths to this surface here, but I take it out to 10 thousandths bigger on the radius, so 20 thousandths bigger on the diameter, just of the tapered part. I start this dimension here, this diameter of the chamfer, in the same place, and I run this straight turn back here, which is the 4.5 inches right here and come out to all these nominal dimensions, but I leave a little bit just on the taper and let it intersect wherever the chamfer and the straight turn would intersect it. And I'll show you that on the part over here. And the gauge, because I have the gauge that gauge this with for the standoff distance of this 0.625 plus 9.8 thousandths minus 5 thousandths, or this is probably plus 10 minus 5 in inches really. So you have to hold a fairly close tolerance on the diameter of this thread, if you will, if there is such a diameter on a tapered thread, because when you gauge it, every 2 thousandths on the diameter here, or 2 thousandths on your wear offset, if you look at it that way, moves this distance 12 thousandths of an inch, because this thread has a, well, they call it a 1 in 6 taper down here on this dimension, but the more normal way that I've seen this dimensioned is a 2 inches and 12 inches, and the other taper that API threads have, it's typical, is a 3 inches and 12 inches. So this is the 2 inches and 12, or if you divide that 2 inches in half from the center line out on the angle, it would be 1 inch and 12 inches. So this would be a ½ inch and 6 inches. It's the same thing. They've just changed it. They've dimensioned it this way for some reason. So given that angle, every 1,000th of an inch on the radius or 2 thousandths on the diameter will move the gauge length 12 thousandths of an inch. So you have to kind of take all this into account when you cut this, and even though some of these dimensions have fairly good tolerances on them, you don't really end up with that much tolerance because of this right here being so close on this thread depth and everything, and you want the insert to top it off. Very important to use the correct insert too, because there's two different angles on API threads, the 2 inches and 12 inch length and the 3 inches and 12 inch length, and if you use the wrong insert, it won't top the thread correctly and put these corner radiuses on the thread correctly. So let's go over to the machine and look at the gauge and how the part gets gauged. Here's the gauge for this particular thread, and you can see, I don't know if you can see that or not. Let me see if you can read it on the right here. It says, if I get it closer, see, it says 0.625 standoff. So that's what you're going for, and you saw the tolerance on the drawing, and so this is a tapered gauge that you just thread on the thread, made specifically for this size thread. So let's put it on the part, and I'll show you the way that this goes on there. Pretty simple to do this. You just stick it on here as far as you can get it, and then you just start threading it up onto there. Kind of let it set on the taper of the thread. And then you just tighten it hand tight. You get a caliper. This isn't that really close. I guess you could stick gauge blocks between here or something, but this is what we're going for, is the 5/8 of an inch standoff between the shoulder and the gauge here. So that's all there is really to gauging it. But like I said earlier, you do have to make sure that the depth of the thread and everything is correct, and what controls that for the most part is the insert itself, the topping insert. You do have to kind of keep an eye on the insert to make sure that the tip of it doesn't wear too much. But there should be nice radiuses cut on the thread when you're finished. You know, there should be no burrs or anything. It really does a pretty nice job. doing it. And also there's a tolerance of to the flank of the last full thread, in this particular case on this drawing, of a 1/2 inch from this face as well. So it's not really that hard of a thread to cut, but it just has to be you know, you just have to pay attention to a few things on here. And in my case, because this thread, well, my part has a this particular part has a counter bore with a shoulder back here that has a dimension going back from the face that's not close. It's plus or minus 10 thousandths, but you can't start cutting off a bunch off the face here and this to get your distance on this particular part. You have to kind of have everything correct and then run your threading tool in until, you know, it starts topping the thread, and until you get the 5/8 gauge distance on the gauge, the way I just showed you. This video is getting a little bit long, and I wanted to show you the machine work of this, and I will, but I think we're going to have to do it in the next video, because this is, I wanted to explain all this because I thought it was important to show you this and about the machine and the clearances on the machine. But I think I'll have to do the machine work itself in the next video on this part. So thanks for watching, and look at the next video to see the machine work.